Alright, welcome back. Let's study a situation where we have two blocks, M1 and M2, M1 bigger than M2, and there is a force applied to M1, directly applied to M1. The two blocks are on a frictionless table. So this problem, the first question that we want to solve is, what is the acceleration of this system? Now this problem is important for two reasons. The first one is because it can teach us about the importance of choosing the object of interest. As we will see, choosing the correct object of interest can simplify a lot the solution of a problem. The second thing is that this problem is going to show us that from a straightforward application of Newton's second law, we can obtain Newton's third law as it applies to the contact forces between the blocks. So let's get started. So to find the acceleration of the object and to solve any physics problem, as we've said, the first thing will be to do a sketch of the situation. I'm already providing you with a sketch, so this part is done. Next thing will be to categorize the problem. Is this going to be a kinematics problem? You might be tempted to say that because there is a question about the acceleration. But notice that there is no information about the velocity, distance traveled by the blocks, time, none of that has been provided. So this is definitely not going to be a kinematics problem. A better category for this problem is Newton's second law problem, because we have a question of acceleration, and obviously this is going to depend on the applied force on the blocks. So the way to connect force and acceleration is through Newton's second law. So let me redraw this to make more space. Third step will be to think about the variables in the problem, what was given and what you're looking for. In a problem like this, without any numerical values given, it is important to realize which of the variables in the problem are given. That is, that if the numerical values of those variables had been given, you should be able to find the answer to the unknowns. So in this problem, f, m1, and m2 are given. You can assume that you know the value of these variables. What you're looking for the first question of the problem is the acceleration. So your answer for the acceleration is going to be a function of the given variables. That is a function of capital F, the applied force, m1 and m2. There shouldn't be any other variables in your answer for the acceleration. Fourth step is to think about the equations and concepts that you can use given the fact that the problem is a Newton's second law problem. Obviously, F equals ma is the first equation that comes to mind. There might be other equations like the equation for kinetic friction, but in this problem, since we have no friction, this equation doesn't really play a role. Now, since we have identified that we need to use Newton's second law to apply the equation F equals ma, the first step is always to identify what's the object of interest. This is actually a crucial question, because when using correctly Newton's second law, the mass has to be the mass of the object of interest. So if you choose m1 as your object of interest, then the mass that you will plug in the equation would be m1. If you choose m2, then it will be m2, and so forth. So should we choose m1 as the object of interest? I'm not going to give you the right answer immediately. I'm just going to explore with you the different possibilities. So suppose that we assume that m1 is the object of interest. Well, if m1 is the object of interest, draw a circle around it. That's your object of interest. And now make a list of all of the objects that are in contact with m1. So in your list, you should include the force F, since it is directly applied to m1. m2 is another object that is touching m1. And finally, the table is touching m1. So those are the three objects that are going to be able to put a force on m1 in addition to the force of gravity. Next step is to use this information to draw your free body diagram for m1. So let's draw a dot in the center of m1, and the normal force between the table and m1 let's call it N1, pointing up of course. I'm going to redraw the force F with its tail at the dot that represents M1. So you want to draw all your vectors with their tails at the object of interest. Then there is the contact force between M2 and M1. That contact force should be perpendicular to the contact surfaces, which in this case are vertical, so the force is going to have to be horizontal, but the force could in principle point to the left or to the right. The force in this case is going to be pointing to the left because this is the force that M2 is applying on M1. M2 cannot pull on M1, it can only push on M1. So since M2 is to the right of M1, pushing on M1 means the force is going to be to the left. And finally, the force of gravity pointing down. So now we have the complete free body diagram. The next step is to write Newton's second law for this object. In the x direction, which is the interesting one for us in this problem, we have the force F positive, the contact force between 2 and 1 being negative because it points to the left, and that's all we have in the x direction. So F minus F2 on 1 should be equal to the mass of the object times its acceleration. Notice that we could have called the acceleration A1, but there is no need to use this index since we know that A1 is going to be equal to A2. The block M1 and the block M2, because of the contact between them and the fact that the force is applied to M1, they're forced to have the same acceleration. If M2 had not the same acceleration, had less acceleration than M1, it would be moving through M1. If you're pushing on this block with a constant force, there is no reason why M2 would accelerate faster than M1. In fact, as soon as M2 loses contact with M1, there will be no force in the horizontal direction accelerating M2. So M2 would move back to make contact with M1. So at all times we expect M1 and M2 in this situation to move together, which means they have the same acceleration, and we have no need to put a 1 to specify that we mean the acceleration of object 1. After writing the equations, you can try to solve for the acceleration, which is, after all, what we're looking for. Now notice that the problem with this approach is that the force that 2 puts on 1 at this point is unknown to us. So we cannot solve for the acceleration since we don't know F2 on 1. You might think that that it is a good answer simply to give a in function of F2 on 1 and M1, but this is incorrect. The solution that we're looking for the acceleration must be a function of capital F, M1 and M2 only. These are the given variables in the problem. Nothing else should show up in your final answer for the acceleration. Now if M1 turned out to be not the right choice to find the acceleration, what other choices do we have? Well, let's choose M2 and see if we have better luck with that. So if M2 is the object of interest, then let's draw a circle around it and do a list of the objects that are in contact with M2. Clearly M1 is in contact with it and the table. Is the force F in contact with M2? Should we include F in the list of objects in contact with M2? Clearly F, as stated in the problem, is acting on M1, is applied directly to M1, not to M2. The effects of F will be felt by M2, but F is not a force that is directly in contact with M2. Therefore, we do not include that in our list. The free body diagram for M2, according to the list of objects, has a force due to the interaction between M1 and M2. The fact that M1 is touching M2 puts a force on M2, and that force should be perpendicular to the contact surfaces, and in this case it should point to the right, since M1 can only push on M2, it cannot pull on it. The force that is related to the contact with the table is normal 2, and a gravitational force of m2g acting on it. So now our free body diagram is complete. We can write the equations that correspond to this free body diagram. In the x direction, we have that the force that 1 puts on 2 is the only force in the x direction. It should be equal to m2 times the acceleration. One more time, since we're looking for the acceleration, this equation doesn't help us because we still don't know what's the contact force that 1 puts on 2. So choosing m2 as your object of interest, again, has not led you to the answer that you're looking for. So what can we do now? To solve this problem, let's think about a slightly different situation. Suppose that we have a solid block with mass m1 plus m2. You could even give it the same shape as the shape of m1 and m2 together. If this block was resting on a frictionless surface and we had the same force as before acting on this block, then what would be the acceleration that this block experiences? Newton's second law says that the force applied to it should be equal to the mass, which is m1 plus m2, times the acceleration, from which you solve that the acceleration is f divided by m1 plus m2. So that's kind of easy. Now let's think about what we have. So the two blocks are in contact with each other. Let's call that situation 1 on top. Situation 2 is the two blocks, same blocks as before, but suppose that you add a drop of glue between the two blocks. So now they're glued together. Situation 3 at the bottom has the block that we just discussed, which is a single piece with mass m1 plus m2. Think about whether you would expect that in situation 1 the acceleration of those two blocks would be different from the acceleration after you add a small drop of glue between them. Should A1 be different from A2? Nonsense. Clearly, adding a drop of glue should not affect in any way the acceleration of the two blocks. The same force is applied, the two blocks have the same, the net mass of the blocks is the same, m1 plus m2. It would be almost magical if you, by adding a drop of glue between two objects, you would be able to change the acceleration as the blocks move together. That doesn't make any sense. So we are forced to conclude that A1 should be equal to A2. Now what is the difference between situation 2 and situation 3? Would you expect that the acceleration in situation 2 is different from acceleration 3? Then again, this is nonsense. The drop of glue has made sure that M1 remains in contact with M2 at all times. They form a single object for all practical purposes. There should not be any difference between an object that has two pieces glued together and an object that has that is made of a single solid piece. So with this analysis, we conclude that the answer for the bottom situation, when the block is a single block of mass m1 plus m2, the acceleration for that case should be the same as the acceleration for our situation with the two separate blocks moving together under the effect of the force F. So the answer to our question for the acceleration should be F divided by m1 plus m2. Now how can you get that answer? By choosing the object of interest. Well, you can choose as your object of interest together m1 and m2. If you do that, then in your list of objects that make contact forces to this object, to the object of interest, you will have the table and you will have the external force F, and that's it. There's no other objects that are touching the object of interest m1 plus m2. So a free body diagram for your system would show the normal and the weight in the vertical direction, and in the horizontal direction only the force F acting on it. which tells you immediately that that force F should be responsible for the acceleration, F equals m1 plus m2 times a, which gives you, as we said before, an acceleration of F divided by m1 plus m2. Now what this is telling us is something important. This problem, this analysis is telling us that if two objects are in contact with each other and they are restricted to move with the same acceleration, they can be considered to be part of a single system with a mass equal to the sum of the masses. This is a strategy that is going to be very useful for you in solving different problems in the future. Now let's propose another question for this system. Let's see that we want to find what is the contact force between the two blocks. There is a contact force that 1 puts on 2, as we said before, and the contact force that 2 puts on 1. We've drawn the two forces before like this. F2 on 1, the force that block 2 puts on block 1 points to the left, and F1 on 2 is the force that 1 puts on 2, and that one is pointing to the right, acting on M2. So how can we find the magnitude of these forces? Once again, we are dealing with Newton's second law, which begs the question of what is the object of interest that you're going to use to solve these questions. We already have said that if you were to choose the object of interest m1 plus m2, then the only external force acting in the x direction is F. Therefore, in your equation for the motion of m1 plus m2, there is no reference to the contact force between those two blocks. Those contact forces cannot change the overall motion of the system. So, object of interest m1 plus m2, it's not going to work. Let's try m1. The list of forces acting on m1 includes the table and m2 and the corresponding F, and the corresponding free body diagram has, we've seen it before, we have F to the right, to the left F2 on 1, normal force up, weight going down. Corresponding to this free body diagram, we can write Newton's second law as F, positive because it goes to the right, minus F2 on 1 because it goes to the left, equals m1 times the acceleration. From this equation we can solve for the force that 2 puts on 1. It should be F minus m1a. We have already solved for the acceleration in the previous step. Therefore we can replace the value of the acceleration, F divided by m1 plus m2, and we get the final answer for the force that 2 puts on 1. After cancelling some terms, we end up with m2f divided by m1 plus m2. m2f divided by m1 plus m2. So we got that answer. Now, what about the force that 1 puts on 2? What should be the object of interest to tackle this question? Clearly, m2 should be the object of interest, since the force 1 on 2 is acting on block 2. So block 2 should be your object of interest. The objects that are touching M2 are M1 and the table. So the forces associated with this are the normal force, the weight, and the force that 1 puts on 2. The equation corresponding to these forces says that in the x direction, F1 on 2 should be equal to M2 times the acceleration. Since we already know how much is the acceleration, then we can simply replace and find the force that 1 puts on 2. The final answer is m2f divided by m1 plus m2. So we have figured out in this problem that the contact forces between these two blocks have equal magnitudes, but they have opposite directions. The contact force that 2 puts on 1 goes to the left. The contact force that 1 puts on 2 goes to the right. So this is, in this problem we can see that by a straightforward application of Newton's second law, to the different parts of the system, we have arrived to a result that is consistent with Newton's third law. Of course, Newton's third law is completely general, and it applies to this case, and it applies to many other different situations. This we're going to discuss in future videos.